In the summer of 1977, humanity launched Voyager 2, a modest spacecraft powered by 1970s technology and a bold dream to explore the outer planets. Few could have imagined that this intrepid probe, now over 12 billion miles from Earth, would rewrite the rules of space science nearly half a century later. Having crossed the Helopause, the invisible boundary where the sun's influence gives way to the vast interstellar medium, Voyager 2 has sent back data that defies every expectation, revealing a cosmic frontier alive with inexplicable phenomena, from magnetic fields that twist in defiance of physics to plasma behaving like nothing we've seen before. These discoveries challenge our understanding of the universe and our place within it. This is the story of Voyager 2's impossible findings, a tale that forces us to rethink the solar system's edge not as a quiet horizon, but as a dynamic, enigmatic gateway to the galaxy. So, buckle up, hit that like and subscribe button, and join us on this journey into the unknown. The Helopause was long thought to be a simple demarcation, a line where the solar wind, a stream of charged particles from the sun slows and merges with the interstellar medium, the sparse gas and dust between stars. Scientists modeled it as a diffuse, somewhat passive transition, a fading of solar dominance into the chaotic void of interstellar space. But Voyager 2, drifting far beyond the planets where sunlight is a mere whisper, has revealed something far more complex. The Helopause is not a static edge, but a vibrant, reactive frontier teeming with forces and structures that defy our best theories. Its instruments, though built in an era of analog circuits and slide rules, have detected anomalies that demand a complete overhaul of astrophysical models. As Voyager crossed this boundary, its sensors began transmitting data that didn't align with decades of predictions. Cosmic rays, magnetic fields, plasma flows, and radio signals all behaved in ways that seemed, at first, impossible. The spacecraft's findings suggest that the Helopause is not merely a fence separating the solar system from the galaxy, but a dynamic membrane, a transformative zone where solar and galactic forces collide, creating conditions unlike anything observed within the heliosphere. These discoveries are not just new data points, they are provocations, urging scientists to question the very scaffolding of space physics. One of the most staggering findings came from Voyager 2's magnetometer, an instrument designed to measure the strength and direction of magnetic fields. Scientists expected the magnetic field beyond the Helopause to be weak, disordered, and dominated by the diffuse interstellar medium. Instead, Voyager found fields that were astonishingly strong, up to 4 times the intensity predicted, and remarkably organized. The field lines were not the chaotic tangle anticipated, but aligned in precise, almost structured patterns, as if sculpted by an unseen force. This was no minor deviation. The magnetic field's strength rivaled that found closer to the sun, and its direction diverged sharply from what Voyager 1, the other interstellar pioneer, had observed years earlier. While Voyager 1 reported a gradual weakening of magnetic influence, Voyager 2's data suggested a region of intense electromagnetic activity, with field lines twisting into helical shapes or converging into stable configurations. This discrepancy raises a profound question. Are the two spacecraft even encountering the same interstellar environment? Or does the Helopause vary dramatically over short cosmic distances? The implications are seismic. Such organized magnetic fields suggest the presence of large-scale structures, perhaps galactic magnetic filaments, or a weight carved by the solar system's motion through the Milky Way. These structures could be relics of ancient stellar processes or part of a broader galactic magnetic skeleton, invisible until now. If the Helopause hosts such features, it challenges the assumption that interstellar space is a formless void, suggesting instead a medium rich with architecture and energy. Some scientists initially suspected an error in Voyager 2's aging. instruments. After all, the spacecraft relies on a fading radioisotope thermoelectric generator and electronics designed before the internet existed. But rigorous checks confirmed the magnetometer was functioning perfectly, its data consistent, across multiple readings. The signals were real, and they described a phenomenon that no simulation had anticipated. This magnetic anomaly forces a reevaluation of how magnetic fields propagate and interact in interstellar space, potentially reshaping our models of galactic dynamics. Voyager 2's cosmic ray subsystem, built to detect high-energy particles from distant stars and cosmic events, revealed another shock. Cosmic rays, protons, and nuclei accelerated by supernovae or other violent phenomena were expected to flow uniformly in interstellar space, free from the sun's influence. Instead, Voyager 2 detected strange surges with particle counts rising and falling in irregular, almost rhythmic waves. More startling was the directional asymmetry. High-energy particles arrived predominantly from one direction, as if funneled by a cosmic lens. This was no random fluctuation. The data showed a persistent bias, with particles bending around the spacecraft as if guided by an unseen force. These weren't solar particles. Their energy signatures pointed to galactic or even extragalactic origins, possibly from distant neutron stars or black holes. The idea that something could focus these particles, perhaps a massive magnetic structure or a gravitational anomaly, defies existing models of interstellar space. No simulation had predicted such a mechanism, and the persistence of this pattern demanded serious attention. The implications are profound. If the Helopause can bend cosmic rays, it might act as a natural shield, protecting the inner solar system from harmful radiation, but this shield is not constant. As the solar system moves through the galaxy, encountering clouds of gas, magnetic fields, or even dark matter, the Heliopause's shape and strength could shift, exposing Earth to increased radiation. Over geological time, such changes might have influenced climate, triggered evolutionary shifts, or even contributed to mass extinctions. Voyager 2's data suggests the solar system is not an isolated bubble, but a dynamic participant in a galactic ecosystem vulnerable to cosmic weather. The plasma environment beyond the Heliopause added another layer of mystery. Plasma, the hot, ionized gas that dominates much of the universe, was expected to be sparse and sluggish in this region, a far cry from the turbulent solar wind within the heliosphere. Yet Voyager 2 found plasma that was denser, colder, and utterly distinct, neither fully solar nor interstellar, but caught in a strange, transitional state. This plasma formed a kind of cosmic buffer, a sheet separating the heliosphere from the true interstellar medium. This unexpected density and temperature profile suggests a previously undetected phase of matter, a hybrid plasma that defies categorization. It's not driven by the sun's heat, yet it's structured to be typical interstellar material. Scientists are now exploring whether this zone represents a stable state, unique to boundary regions, or a temporary phase shaped by the interplay of solar and galactic forces. The discovery opens a new frontier in plasma physics, with potential implications for understanding cosmic matter across the universe. The plasma's behavior also hints at a protective role. If this buffer zone can modulate particle flows or absorb energy, it might act as a cosmic filter, shielding the inner planets from galactic radiation. But its variability evident in Voyager 2's fluctuating readings suggests this shield is dynamic, potentially weakening or strengthening as the solar system encounters different interstellar conditions. This could have far-reaching consequences for planetary habitability, influencing everything from atmospheric chemistry to biological evolution. Voyager 2's radio transmissions, sent across billions of miles to Earth, carried their own surprises. As the spacecraft pinged signals back, scientists noticed subtle distortions, frequency shifts, and phase modulations that didn't match expectations for a homogeneous interstellar medium. These anomalies suggest the signals were passing through complex plasma structures, like eddies, folds, or layered sheets, that bent and twisted the radio waves. This implies the heliopause is not a smooth boundary, but a turbulent, reactive frontier, sculpted by forces we don't yet fully understand. The distortions could be caused by galactic currents, remnants of ancient shock waves, or even interactions with distant stellar remnants. If these structures exist, they point to a heliopause that's less like a fence and more like a semi-permeable membrane, actively shaping the flow of energy and matter between the solar system and the galaxy. These findings have practical implications. Understanding how radio waves propagate in this region could improve communication systems for future interstellar missions. More broadly, the presence of such structures suggests interstellar space is far from empty. It's a dynamic medium, rich with invisible architectures that influence everything from particle paths to electromagnetic fields. Among the most dramatic discoveries were signs of magnetic reconnection events, sudden, explosive realignments of magnetic field lines that release bursts of energy. Such events are common near stars or black holes, where intense magnetic fields drive powerful dynamics. But in the supposedly calm expanse beyond the heliopause, that was unthinkable. Yet Voyager 2's instruments detected rapid shifts in magnetic polarity, accompanied by energy spikes that echoed the violence of stellar processes. These reconnections suggest the heliopause is a hotbed of electromagnetic activity, driven not just by the sun but by interactions with the galactic environment. The energy released could accelerate particles, shape plasma flows, or even generate the mysterious structures Voyager 2 observed. This challenges the notion of the solar system's edge as a passive region, revealing it as a frontier where cosmic forces collide with unexpected intensity. The implications extend to space weather. If the heliopause hosts such events, it could amplify or dampen the flow of high-energy particles toward Earth, affecting everything from satellite operations to auroral displays. Understanding these dynamics could be critical for future missions, especially as humanity dreams of venturing beyond the solar system. Voyager 2's instruments also detected chemical anomalies that deepen the mystery the spacecraft found unexpected. Concentrations of heavy ions, calcium, iron, and even traces of carbon-based molecules far higher than predicted for this region. These ions bear the signatures of distant stellar events, possibly supernovae that exploded millions of years ago. Their remnants carried by galactic winds to the solar system's edge. Dust grains, too, were unlike anything seen within the heliosphere. Small, irregular, and coated with what might be organic films or frozen volatiles, these grains sparked secondary emissions when struck by high-energy particles. This dust-plasma coupling suggests the heliopause is a chemical crucible, a place where the building blocks of planets and perhaps life are forged. The presence of organic precursors raises tantalizing questions. Could this boundary zone be a nursery for the chemical seeds of life, not just for Earth, but for countless other worlds? These findings challenge our understanding of cosmic chemistry. If the heliopause is enriched with heavy elements and complex molecules, it suggests interstellar space is a dynamic mixing pot where the ashes of dead stars blend with the solar system's outskirts. This could reshape theories of planetary formation and the distribution of life's raw materials across the galaxy. Voyager 2's data revealed temporal and spatial anomalies that further complicate the picture. Particle densities fluctuated in cyclic patterns as if the interstellar medium were pulsing to an unseen rhythm. These oscillations don't align with solar cycles or known galactic phenomena, suggesting a larger, unidentified influence, perhaps ripples from ancient gravitational disturbances, or even dark matter structures. Spatially, the heliopause is far from uniform. Voyager detected abrupt changes in magnetic field orientation and temperature, sometimes over mere kilometers. These field discontinuities and temperature spikes suggest microscale boundaries or shock fronts analogous to weather systems. On Earth, the heliosphere itself appears lopsided, compressed in some areas and diffuse in others, as if molded by external pressures from interstellar clouds or magnetic anomalies. These findings point to a multi-phase environment where plasma, particles, and fields interact in complex, non-linear ways. The heliopause's asymmetry could be driven by galactic-scale forces, such as shock waves from distant supernovae or the solar system's motion through a structured interstellar medium. Understanding this complexity is crucial for modeling the solar system's interaction with the galaxy. Perhaps the most haunting discovery was the detection of low-frequency electromagnetic waves, or plasma tones, within the interstellar medium. When converted to sound, these waves form eerie, harmonic patterns like the vibrations of a cosmic orchestra. Their coherence suggests the plasma is confined or reflected, possibly by vast magnetic scaffolds or boundaries we cannot directly observe. These plasma waves behave like standing waves in a confined system, implying that interstellar space is not a chaotic void, but a resonant medium capable of carrying energy and information across vast distances. If stable, these waves could one day guide interstellar spacecraft, offering a natural propulsion system. For now, they challenge our understanding of how energy propagates in the galaxy, suggesting a medium rich with invisible dynamics. Voyager 2's data hints at physics beyond our current frameworks. Subtle deflections in particle paths suggest interactions that neither general relativity nor standard electromagnetism can fully explain. These could be signs of unknown force carriers, quantum scale effects, or even the influence of dark matter, which might cluster in filaments that subtly warp spacetime or magnetic fields. The spacecraft's endurance itself is a scientific treasure. Its exposure to decades of cosmic radiation, particle impacts, and dust erosion provides a unique data set for material science, informing the design of future interstellar missions and our understanding of how objects like comets or rogue planets weather the interstellar environment. Voyager 2's discoveries blur the concept of boundaries. If the heliopause is a reactive, dynamic zone, where does the solar system end? The idea of a continuum where solar and galactic influences intertwine challenges our sense of cosmic isolation. The heliopause may act as a cosmic shield, modulating radiation that reaches Earth, with implications for climate, evolution, and habitability. Its variability suggests that Earth's cosmic environment has shifted over millennia, potentially leaving traces in geological records. The chemical richness of this region raises profound questions about life's origins. If the heliopause fosters organic precursors, it could be a universal crucible, seeding the galaxy with the building blocks of life. This positions the solar system as an active participant in a galactic ecosystem, not a solitary island. Practically, these findings have immediate relevance. Understanding the heliopause's dynamics could improve space weather forecasting, protecting satellites and astronauts from cosmic radiation. The structured plasma waves and magnetic fields suggest possibilities for future propulsion or navigation systems, turning interstellar space into a highway rather than a barrier. Voyager 2, a relic of the Cold War, was never meant to deliver such profound revelations this late in its life. Its golden record, carrying greetings from Earth, symbolizes humanity's curiosity, a curiosity now rewarded with data that rewrites astrophysics. Each faint signal from this aging probe is a spark, igniting new questions about the universe, its boundaries, and our place within it. The heliopause, once a distant horizon, is now a vibrant frontier, alive with magnetic storms, chemical crucibles, and cosmic harmonies. Voyager 2's discoveries remind us that the universe is not a static map but a dynamic, unpredictable realm. As we analyze its data, we're forced to rethink not just the solar system but the galaxy itself, embracing a cosmos far stranger and more connected than we ever imagined. So, what do you think of Voyager 2's cosmic revelations? Share your thoughts in the comments, give this video a like, and subscribe for more updates from the edge of the solar system. Voyager 2 is still out there, drifting through the stars, whispering secrets that challenge our understanding and inspire our dreams. The universe is calling, let's keep listening.